Hi everyone. So I'm going to wrap up my discussion of light here, light waves specifically on this, on a couple of additional properties of light I want to focus on because that's going to be important when we're discussing some of the discoveries prior to quantum mechanics. So one of the important properties of light that we you need to understand is this property called interference of light. And what happens is that if you have waves, okay, two waves, and these waves are what we refer to as being in phase, and really what that means is that the peaks of, the peak of one wave aligns exactly with the peak of the other wave. That's what we refer to as being in phase, and the trough aligns with the other trough. What happens is that when waves are in phase together, they can interfere with each other, and that's referred to as constructive interference when they're in phase with each other. And what that means is that the waves can basically add, so the two waves add with each other. So the part that's the peaks add together to form a new wave that's has twice the amplitude as the previous wave, as the original wave. And then the troughs, as you can see here, also add together to form a wave that has a new wave that has twice the trough from the compared to the original wave. So that's what we refer to as constructive interference. So in terms of light, what you expect to see, of course, is that, remember, amplitude corresponds to brightness, right? So if you have a light wave that's twice the amplitude than what you have originally, you should see a light, either a light spot or a light, on a detector that should be twice as bright as the light that you saw originally. I'll give you an example of this in a second, okay? On the other hand, the waves could also interfere with each other if they're out of phase. Okay, so what do I mean by out of phase? What I mean is that the peak of one wave aligns with the trough of the other wave, and vice versa. The trough of the first wave aligns with the peak of the second wave. If you have that, when you add these two waves together, then it results in basically a wave that has no signal whatsoever, because all these parts cancel out with each other. So this is what we refer to as destructive interference. Now, you don't have to be exactly, what we call 180 degrees out of phase. You might be out of phase only slightly. So if you just shift this wave a little bit to the left of the top wave, then you get a slight out of phase between the two waves. So you're going to get partial destructive interference. So the signal of the resulting wave is going to be less than the original wave, but it's not going to be completely knocked out like this one. Okay? All right. So the next property I want to talk about associated with interference is something referred to as diffraction. So diffraction is basically a bending of light when light encounters either an opening like this. So let's say you have what we often call a slit. So you have an opening here, which is your slit. So if you have a light source from this side, and the light source hits this opening, then it's going to bend around that opening. And if you have another opening here, that light is also going to bend. And when the light is being bent, and the light waves that are being generated on this side starts to interfere with each other, whether constructively or destructively, then what you'll see here on the screen, if you have a projector or a detector that detects the light that hits that that has been diffracted, you start to see a pattern, and the pattern is what we refer to as a diffraction pattern on this film. And the pattern is usually a dark, a very strong intense light, followed by no light, followed by intense light, followed by no light, and so on. So that's what we refer to as a diffraction pattern. It's actually shown here as well. So the strong pattern basically corresponds to the constructive interference, and then the no light pattern corresponds to destructive interference. Okay. You actually see this when you have a diffraction grating like this. So this is referred to as a diffraction grating when you have something that has a lot of holes in them, the light can be bent in such a way to generate all kinds of diffraction pattern. So let me just show you a quick video of what this thing looks like. So I want to show real quick here is a video on diffraction grating and laser light source. So basically what this person is going to do is he's going to hold up a series of diffraction grating, and you can probably kind of see it here. So this is a diffraction grating right here. So the microstructure of this thing is really that it's composed of, you know, a lot of small holes. The same way as this picture I showed you earlier, you know, on the slide before, which is sort of like a bunch of these small holes, of course, all set up in this one glass material or this plastic material that he's holding right here. Okay, so that's the diffraction grating. So what he's going to do is he's going to shine light on one side to hit this diffraction grating, and what you're going to see on the other side is the diffraction pattern that's generated by that diffraction grating. Okay, so you can see here, here's the laser light, and you see what happens is now he shined that light through the diffraction grating, and you see this whole pattern right here that forms as a result of light being diffracted by that diffraction grating. And I want to point out here that you see some of these light spots is very strong. In fact, stronger probably than what his original light was. Remember that the original light was right here. Okay, so here's where before the diffraction grating was being put in front of it, the light was right here, right? And then once you put it through the diffraction grating, you see some of these spots that are a lot stronger than what the original light was. But you also see some of the spots that are weaker, and in fact you see some of these part here of the diffraction pattern is completely empty, which means that there's no diffraction. So that's what I meant earlier about the fact that you're gonna get this on and off pattern repeats of constructive interference and partially destructive interference and completely destructive interference here. Okay, so you see that pattern with this particular diffraction grating right here. Okay, you see very strong interference and then, you know, weaker interference right here. Now he's going to use a different diffraction grating, and similarly he's going to shine light on that, and you can see that here's the pattern right here, right? So you can see pretty clearly here there's some that are really strong and there's some that are weaker. Okay, so that's a very typical diffraction pattern you'll see using a diffraction grating. Okay, again, here's the original light. I want to point out here's the original light, and earlier of course he showed light that has been diffracted. Here's the diffracted light. Okay, now you can do this with all kinds of light waves. It doesn't have to be blue, right? So you'll see that he's going to show you here all the different diffraction grating here, and he's going to show it with this light. This is the diffraction pattern. With this grating, that's the diffraction pattern. He's going to show you with another diffraction grating. You get this pattern, and so on. So one of the things I want to point out, actually, the importance of this is if you go back to this slide right here on the lecture slide. Okay, oops, just moved that picture right there. But if I go back to the lecture slide, I point out here at the bottom, I made this statement, which is that when light is shined on a crystal, so what is a crystal? A crystal is basically a three-dimensional arrangement of atoms and molecules. Okay, so if I have diamond, for example, the diamond crystal, okay, a diamond that you have in front of you, it's basically a three-dimensional arrangement of carbon atoms. So the carbon atoms is arranged in a certain way. And what happens, what people found out was that if you were to shine light on that crystal, you get exactly the same type of diffraction pattern. You get the pattern that you would have gotten if you just have a bunch of holes here in the diffraction grating. Okay, so the atoms in the crystal acts pretty much as your slits or your holes in the diffraction grating. Now what's interesting about that is not so much that you get diffraction pattern out of the crystal, but it turns out what's interesting about it is that if the diffraction pattern you get as a result of shining light on that crystal depends on how the atoms are arranged in the crystal. Okay, so if you have a particular arrangement, you're going to get one type of diffraction pattern. If you get a different type of arrangement, you're going to get a different type of diffraction pattern. And that becomes a really useful information, because what that allows us to do is, if we're able to model what the atoms look like here, we should be able to predict what diffraction pattern we would see. Okay, and that's really how people started to determine what sodium chloride looks like, and of course later on what biological molecules look like DNA, for example. That's how people started to determine how DNA looks like, and why, how we know that DNA is a double helix, because we were able to shine light on a DNA crystal and notice that there's a certain diffraction pattern, and working backwards we can determine what DNA looks like. Okay. Again, going back to this diffraction grading, if you have a certain shape like this, if you have a shape that looks like this, right? Basically, that particular diffraction pattern depends on what the grading looks like. So if the grading looks like a certain shape, a certain type of structure, then you're going to see a particular diffraction grading. And that's what I meant by you can determine the structure of the molecule that makes up the crystal by looking at the diffraction pattern. Okay. So going back to the slide itself, I want to, at the end, really kind of summarize some of these information we talked about in this section. First off, the idea is that the physical world can be modeled really as either particles or waves. In this section, we really talk only about waves, because that's what is going to help us understand quantum mechanics. Now, a wave has the following properties, as I mentioned. Yeah, you have speed, you have wavelength, you have frequency, and you have amplitude. So you need to know what these things mean. Light, which is what we're interested in, is classically, okay, in classical physics, is modeled as an electromagnetic wave. Okay, as a wave that consists of both electric and magnetic waves. The color of the light is what we call the wavelength of that light, and the brightness of the light is the amplitude of the light wave. Okay. Now, we also talk about the fact that light has a huge range of wavelength. The part that we see is really just the visible light, but the entire range of the light waves that are available is referred to as the electromagnetic spectrum. A prism or raindrops or similar devices can be used basically to split white light or sunlight into its constituent waves, into component waves. Okay, and we just finished off just now with talking about a couple of properties of light that are going to be important in understanding quantum mechanics, which is interference of light, both constructive and destructive, as well as diffraction of light.